Hello, everybody. Thank you for making the time to attend my talk. What I'd like to talk to you about today is some of our recent advances in using monolithic quantum photonic sources, particularly for sensing applications. So, this work has been carried out uh, predominantly by my group members, some of whom are actually written up top: Han, Ryan, um, How You, Eric, and Zach. But also, some of this work has been done in collaboration with the RDC and NRC in Canada. So the talk outline looks like so. I would like to introduce the topic of why sensing and why quantum, and I'd like to discuss with you some of the recent developments, particularly in protocols associated with quantum illumination. And in doing so, that serves as an introduction to some of the alternative techniques that we use for target detection that utilize quantum correlations but not strictly quantum illumination. But at the end of that section, I'm going to actually introduce you to some novel quantum illumination protocols that we have recently developed. And then at the very end, I would like to take you through maybe a 5-10 minute overview of some of the technological advances that we have developed and have in house that can actually enable some of these applications. So, why target detection? Why imaging? Why quantum in some respects? Well, I mean, it comes really from both directions. The hardware capabilities with respect to single photo detection, with respect to entangled sources, have been improving significantly. But then again, on the opposite side, there's been a lot of pull and unmet demands when it comes to applications associated with LiDAR, for example, predominantly for noise resilience and some of the of noise resilience afforded through some of the quantum imaging protocols. And the notion that quantum optics utilizes low photon level because of its loss resilience. And again, I'm speaking about protocols akin to quantum illumination that makes them very suitable for applications associated with quantum imaging because quantum bioimaging, sorry, because of the possibilities of avoiding bleaching when it comes to uh, illuminating a sample rather than illuminating it with a high power femtosecond pulse to be able to get sufficient signal to noise ratio. So, what would quantum imaging do when we end up utilizing in these applications? For those of us who are not familiar with the field, they provide enhanced signal to noise ratio, particularly for objects of low contrast. But then, as I've been highlighting, they really provide you with substantial resilience to noise in the environment as well as loss. And this is probably one of the few protocols in quantum that is loss resilient. Everything else, as I'm sure you're more familiar than I am, is extremely sensitive to photon loss as it actually deteriorates the quantum state. Some of the states associated with squeezed states can actually provide us also with subshot noise performance, and that could be advantageous to enhancing the sensitivity of the detection beyond the quantum limit. Perhaps the golden standard of target detection that has been around for the last 10 years or so has been developed by Seth Lloyd at MIT when his seminal science paper spoke about how can one have up to 6 dBs of enhancement in SNR by using entangled states of light. And in 2015, a few years later, this there was the first demonstration of entanglement enhanced imaging through quantum illumination, and that work was carried out by his colleague Jeff Shapiro, and they show 20% enhancement in the signal to noise ratio, as well as 75 dB enhancement in the noise resilience, and that was pretty substantial. But when you come to see this protocol and how it was implemented, it was relatively elaborate setup. It was not all amenable to integration, although it's not impossible to see this being integrated in some sort of fiber setting. But the aspect that makes it particularly problematic for practical sensing applications is that it was all phase coherent and it required some sort of active alignment of the setup to maintain the alignment to within a wavelength. given the phase coherence. So if you're trying to look for sort of objects where you don't know where they are for applications such as LiDAR, as I motivated, you will not really be able to utilize this suite of protocols with great ease, if at all. So this really serves as some sort of introduction to what I wanted to talk to you about. What I wanted to talk to you about is quantum enhanced target detection that does not utilize quantum illumination strictly, but it does actually utilize quantum correlations. So, and that in doing that, that makes the system actually not phase coherent, and it does not predicate or rely on some sort of quantum memory to save the idler. So how does that work? It works like so. You would have some sort of source like four-wave mixing based parametric diamond conversion, or Chi2 based. In our case, as I will show you later, we predominantly use Chi2. And this source of entangled photons generates photon pairs. We split these pairs and we take the signal photon and we get it to interact with the object, and we store locally the idler photon for processing and correlation with the idler photon, the signal photon that has interacted with the object. And that's where the sensing takes place. So the idea is that we would like to use the correlation and the entanglement to help us distinguish the signal from the background noise. And we do that by correlating it with the idler, which we have stored. So that's predominantly what we do. There are two modalities that I would like to talk to you about with respect to the correlation enhanced target detection, which is the column on the right. One of them relates to intensity correlations, and the other one it relates to time and frequency correlations. This is in contrast to quantum illumination, which speaks about the coherent detection of phase quadrature entanglement. And because of we detect phase quadrature entanglement, then we require some sort of phase sensitivity at the setup, as well as the quantum, the ability to store the quantum state and have some sort of quantum memory. So the topics that we have pursued, because they are phase insensitive and because they are useful for applications such as LiDAR, quantum enhanced LiDAR, is intensity correlations, where we actually pump with a pulsed pump SPDC source and we look for intensity correlations through the G11 number as shown below, and I will actually elaborate on that in a minute. The temporal correlations, in contrast, they actually can use pulsed or CW, and we utilize the temporal correlations that are embedded in the photon pair generated, and these correlations are generated through the phase matching process, or shaped, if you like, through the phase matching process. So how do we do that? We actually we use chip sources that we've been developing over the last 10 years or so in the group, and we use these to generate through Chi2 based SPDC signal and idler of a wide range of attributes, as I will speak to you towards the end of the talk, to carry out both intensity correlation and time frequency correlation. These sources could also are being also used to actually demonstrate sort of bona fide quantum illumination protocols, but I'm not ready to talk about this work today. So these sources are chip based and they are fairly compact. They are alignment free, fiber pigtailed in a sort of a butterfly mount. They're based on gallium arsenide systems, a material system, and they offer incredible amount of flexibility in engineering the quantum state through dispersion engineering, group velocity dispersion engineering, as well as group velocity mismatch engineering. And these in turn actually allow us to generate the JSA, the joint spectral amplitude state that's coming out. So intensity correlation, to start, can be quantified as the second order cross correlation, the G11, which is much stronger than the intensity than its counterpart in the classical case. For thermal light, for example, or like, for thermal light, that's probably the best example. As the G11 increases, this provides strong correlation that facilitates facilitate for us the effective discrimination between the signal and the noise photons. A setup that we have used to demonstrate that particular intensity correlation looks like so. So we have a pump that pumps the SPDC process in our chips, and then we have in-fiber based target detection system where the target itself could be actually a beam splitter or anything of the sort that partially reflects the light. And then we get the signal and idler to be coincidentally detected at the photon pairs, the detector pairs. We provide a controllable and measurable amount of noise, and we use an amplitude spontaneous emission noise from that from an amplifier, and we actually also generate a measurable amount of loss. So the figure of merit when it comes to intensity correlation relates to basically the covariance between the signal and idler, and the visibility itself is what we see as some sort of a figure of merit, and that's the contrast of that covariance value. So we correlate that, or we compare that with classical thermal right, if you like, where we get a thermal state and we look at the brightness of that state. If you look at the results from this work, you'll find that this contrast that I spoke to you about for the quantum light, which is the dark black, the black solid line, has a much higher contrast by a factor of 4 and up to when you look at the right hand side plot, up to actually 20 dBs when it compares to the dashed blue line, which relates to the classical light. So this contrast, which we've discussed in the previous slide, is calculated both for thermal light and the dashed blue line at the bottom, and for the entangled state that I spoke to you in the black line. So if you look at the ratio between these two visibility numbers in decibels, you'll find that as the photon flux decreases, that contrast ratio actually increases. And one of the drawbacks of that system is that if you increase that photon pair, if you increase the flux itself, you'll find that the quantum advantage starts to dissipate. If you look at the object visibility again as a function of the noise, you'll find that the contrast is upheld or maintained for the quantum light, which is the black solid line shown up top, when it compares to the dashed blue line, which is at the bottom. Again, this shows the quantum advantage in maintaining the contrast of the visibility as the noise level is increased. This is a log scale and the x-axis. So there's a significant increase in the losses, in the noise. So the intensity correlations does give us up to 20 dB advantage, but the problem with it is that it really is most effective in the low brightness regime. And so what does one do to actually circumvent these limitations? One can actually create a number of photon pair states on different frequency mode pairs, so that one can increase the effective brightness, but then not compromise the single channel photon flux. So then the advantage remains high. However, sort of beyond intensity correlation, thankfully that's not the only correlation that one can obtain from such sources. One can use temporal correlations from these sources. And there is another step further that I would like to touch upon towards the end, where one can actually utilize temporal correlations along with frequency correlations simultaneously. So just out of completeness, our colleagues in NRC have actually recently published work where they have looked at temporal and spectral correlations for the benefit of imaging, and they've looked at independent and simultaneous measurement of time and frequency correlation using single photon spectrometers. So these are frequency resolved single photon counters. However, the time and the frequency of a single photon cannot be measured accurately simultaneously. It's almost like as you improve in one degree of freedom, you lose in the other. So this really limits the performance that you can get from this scheme. But we do have a solution for that. So when it comes to temporal correlations, the proven we use the fact that the probe and reference photons are almost always detected simultaneously, or almost so. So the detection time of each one of these photons is random. However, the correlation between them could be quantified, it could be used. So what we have done actually is taken the target detection using temporal correlation as a transmission estimation problem. So we look at the transmission of the probe photon, and this basically will need to take into account the losses and also the target reflectivity as well as the detection efficiency. So if one can quantify and calibrate the detection efficiency and the losses of the system, one can actually detect the reflectivity of a given target and establish its presence or otherwise. So the accuracy of this estimation, which tells you, which is a figure of merit effectively for this measurement scheme, relates to the Fisher information of the photon transmission efficiency eta p. So we really need to quantify a few, if you like, numbers. So we need to define and quantify the single channel photon detection events, the NP and NR, as well as NC as well. This is for the three different events, but also we would like to quantify the rate of different events as well. P sub P, P sub R, and P sub C. C for coincidence, and R for reference, and P for the probe photon. And once we do that, these are the numbers that gets us to calculate P sub C and P sub, the equations that get us to calculate P sub C, P sub P, and P sub R, as well as the eta P, which is the maximum likelihood estimation of the total probe transmission, and that is directly related to the figure information. So when we formulate this problem in an information theoretic approach like that, one of the big advantages is that we have a significant control in the figure of merit of that protocol in the attributes of the source. And that's something that we can control, and that's something that we have a very good handle on. So this is the, after doing all that work and quantifying the rates of events and quantifying the, for the probe, the reference, and the coincidence, the efficient information formula looks like so, I. So the contribution of coincidence detection events, NC, dominate in the Fisher information expressions. That's really the dominant contribution. The effect of the noise to the Fisher information is proportional to the temporal coincidence window. And you could see that the temporal coincidence window is really the temporal filtering function that is carried out through the entanglement. Practically speaking, the TC is really limited by the instrumentation, the detected temporal resolution, and the intrinsic temporal correlation, which is usually much lower than the detector resolution, and it's also fairly versatile, as we have control on the GVD and the GVM. We've shown, and we know how to, we can make the intrinsic temporal correlation down to 2-3 cycles, optical cycles that is, so a couple of tens of femtoseconds. So let me show you some of the results that we've also achieved about target detection, for target detection using temporal correlations. The setup is almost identical. We always have a target of different reflectivity. We always have a quantifiable noise and loss that we can inject, so we can characterize the system. So if you look at the experimental results, the initial part is shown on the bottom right, which is really the plot of the estimation variance, which is directly related to the Fisher information as a function of the noise flux. So it's really the noise resilience that we're most interested in for the aforementioned reasons that I spoke early on motivating this work. So if you look at the classical light in the log-log plot on the right hand side, it's actually linear. As the estimation, as the noise flux increases, the estimation variance also increases. So the detection precision effectively deteriorates. But at the same time, there is a parametric plot which shows you the quantum performance, the blue, the green, the orange lines, but for different TC. And basically, as the temporal resolution of the system TC changes, the performance, the estimation value changes. And it's obviously much better, lower estimation value as a function of increasing noise when the temporal correlation is shorter. That's understandable. If you look at the ratio between both the variance of the classical versus quantum, you find that we can achieve, given the instrumentation we have, which affords us about TC of 200 picoseconds, we can achieve about 20 dB advantage. So a 100-time improvement over the classical performance using the quantum detection. That is sustained over a much larger range of photon fluxes when it compares to the intensity correlations. That's why it's more superior. Um, one of the advantages of, or one of the important attributes of this target detection system is it can actually inspire us to see what can be achieved if we can convert the photons to the microwave for radar system. And radar has got some figures of merit that are slightly different than those of your typical optical regime LiDAR and typical quantum illumination protocols. So without going through the math, if you look at, for example, the receiver operating characteristics, which is the typical, most standard way of looking at uh, assessing the performance of a radar, you'll find that it's basically nothing but, this is the ROC, is nothing by the detection probability and how it holds. You would like the detection probability to be as close as possible to one, and how that actually holds as the false alarm probability is reduced. So you find that as you reduce the false alarm probability, the detection probability itself actually degrades significantly fast for the classical light, which is the dark, which is the black solid line. But if you look at the blue and the red lines, solid also, you'll find that they are actually those for the quantum light, and there is significant enhancement over that of the classical light. That's just another figure of merit that is much more um, common to radar engineers. One of the most important points that relate to temporal correlations, the fact that it uses CW light, it still contains a wealth of temporal information by definition. And what this affords us is to use CW light of quantum state that looks pretty much like noise, and you could use that to actually do quantum ranging. So we've built up a setup similar to the one that I showed you before, but it was in free space, and it afforded us through an optical telescope to be able to detect a target using this quantum enhanced protocol, but this target could be at different distances. So we could do sort of basically quantum ranging. And as you can see, the estimated, so the transmission estimate exists for different round trip times as we change the position of the target. So as you bring the target farther and farther away from the detector, the transmission estimate happens at a different round trip time. And from that, you can actually estimate the how far the target is. So if you look at the plot here, you'll find the solid gray line tells you the distance that we physically measured for the target. And if you look at the orange plots with error bars, they are actually the distance we've calculated from a completely CW light that involves very few photons streamed out, and from the temporal correlations we can get quantum ranging. That is of extreme interest to the radar community. We have also technologies that we would like to sort of start pursuing that can convert photons from the optical regime to the terahertz and possibly also the microwave. So we can implement all that in a radar setting, if you will. So from correlations to entanglement, what I would like to talk to you about here is another protocol that is inspired from what I discussed about intensity and temporal correlations, but it is actually a legitimate quantum illumination protocol. So what is that based on? In principle, temporal correlations and frequency anticorrelation can be simultaneously measured to an arbitrary accuracy. However, the time difference and the frequency sum of the two photons has to be measured without measuring the time and the frequency of each individual photon, that's respectively. Let's see what happens when we actually use that notion with some frequency generation. So some intuition about SFG is in order here. SFG can only take place when two photons arrive simultaneously, or almost so. So given the energy conservation, which requires the energy of the frequency of the signal and the either to be that equal of the photon, then you know that when Ws plus Wi is equal to Wp, then Ts minus Ti is approximately 0, which can then generate SFG. So how can this be utilized for quantum illumination? In quantum illumination protocol that involves SFG and the time difference and frequency difference measurement, as we've discussed, only the signal photon that is time frequency entangled with the idler photon can generate SFG. So it's kind of a more effective filtering mechanism because of that condition dictated by SFG. And noise photons can hardly generate an SFG given the correlations required in frequency and time. So in the detection process, the photon counting of the SFG generated is only because of the SPDC pump mode. So this can allow us to actually provide simultaneous filtering in the time and the frequency, which cannot be achieved for classical light. Entanglement is required, and this protocol that I discussed with you, which will come out in quantum information in a month or so, is detailed. So what are the results or the ultimate performance advantage that we get out of this new quantum illumination protocol? The fact that it actually outperforms the coherent state target detection in the limit of large entanglement and very high noise background. So it is actually not dictated by any photon flux requirements like the intensity and temporal correlations, and indeed has a superior performance for the resilience against noise when it compares to the coherent state imaging. So what I would like to talk to you about next is the platform that we use to implement all that. So we use compound semiconductors, and it is somewhat less intuitive because it's very high loss. However, it has many a lot of superlatives, if you will. It's some of the largest nonlinear coefficients. It's got very mature fab technology where we could do great things in these, but the dispersion control also is significant. However, we could also integrate the pumps within the same platform, as I will show you, but this all comes with the challenges of basically losses, propagation losses, as well as input and output coupling losses, which are also losses, but also you cannot operate at huge amounts of optical flux because of the third order nonlinearity losses, which is two-fold absorption. What we do as a group, our strategy is basically to use this semiconductor platform to generate and tailor and engineer quantum states of light for many applications. Sensors is one, as I mentioned to you before, through the noise resilient detection, but also enhanced interferometry through squeezed states of light. We use standard semiconductor fabrication technology to achieve these. So these devices are alignment free. They're fabricated using, you could do them using even multi-project wafers, etc., etc. So they're extremely practical, but then you will see how versatile they can be. So the platform that we use is a semiconductor vertical architecture that involves Bragg stacks. It very much looks like a vertical cavity laser, if you know that sort of structure, but you can analytically, almost analytically, calculate the nonlinear coefficient, the JSA of the state, and you could tailor just about every aspect, temporal, frequency, spatial attributes of the state. So this could be extremely valuable for hyperentangled states with engineered um, JSA. The structures look like so, but then these structures, because they look like a VXL, you could also build some sort of the pump of whatever process you'd like to generate also within the same structure. To show you a typical battery operated entangled photon pair source, all of the filtering, the engineering of the dispersion, etc., is all embedded inside of that diode laser. That diode laser is battery operated. Within it, you can actually generate the pump itself through band-to-band sort of recombination, and a laser photon is generated. But then the parametric process is also engineered to generate a quantum state, as you can see from the tomography data below. And the coincidence counts is shown on the plot on the top right hand side. These particular sources are very important for sensing because they're extremely tunable in frequency. So this is an example where we can generate a state that has a relatively broadband JSA, as shown on the plot on the bottom. And when you generate the state, you can actually provide very or relatively broadband entangled state within the S and the C and the L band of 1550 with incredible amount of concurrence of above 98% over 100 nanometer or so without changing a single parameter, with only using the dispersion. No moving parts, nothing. If you start to add extra processes such as extra contacts in the multi-section device to tune the phase, etc., you can even increase that tunability much further. Why is that important? It's important because of sensing application. The sensing itself could be achieved using different techniques. This is an example of actually a difference frequency generation, where the pump is generated for the signal inside of the cavity itself. So you don't really need to bring in the pump from outside like passive devices. One of the huge attractive features of this material system is that it's transparent from about 800 nanometers all the way up to 15 microns. So here is a sort of a time frequency entangled state where the pump itself is around 950 nanometers and the signal is around 2.5 to 2.4 microns and the idler is around 1550. So that's attractive for numerous sensing and ghost imaging applications. You could do further. You can actually end up starting to have the signal and idler straddle the region of the 2 micron and 7 to 8 micron, where the explosive range of fingerprints exists from 7 to 10, while pumping around 1550. There is a discrepancy between the theory, which are the lines in this plot, and the points, which are the measured data, simply because the refractive index of these materials around 7-8 microns is not known to the third and the fourth decimal point as it is at 1550. I think this is all the time I have. So just to sum up, I showed you a couple of intensity and temporal correlation protocols that go beyond quantum illumination. And in contrast to existing quantum illumination systems, these can provide 40 dB enhancement, 30 dB enhancement in the figure of merit, if you like, being the estimation variance or being the visibility, without the need of phase stabilization. And that's a great practical need. I've also gone through, albeit very briefly, I've gone through some of the properties and attributes of the technological platform that we use to achieve these. It is particularly attractive because we have an approach to actually connect the microwave regime to the optical regime, but at the same time, this is not something we pursue currently. Thank you so very much for listening and coming to the talk.